Okay, good morning, everybody. Thank you for coming. I think with timetable for about an hour and a half, we'll probably only need 45 minutes, so you'll all hopefully get away fairly soon. We'll see. So if you don't know me, haven't met me yet, my name's Peter Wynne. It's my email address. If you have any problems with the module, please feel free to email me about this. I'm recording this lecture today. I don't suppose any of you will ever need to watch it, but it should come up online, and I'll point you to where that will be recorded. And so I'm leading up this course, BioM 13. It's a course about different research techniques. It's going to be examined through two pieces of work. We're going to have one test, which will be 50% of the mark, and that will be sometime just before or just after Easter, probably just after the Easter holiday. And then we've got this research techniques essay, which is the other 50% of the mark, 3,000 words, which will be due in sometime in the spring term. I can't remember the exact date. We probably haven't set the date yet for you to hand that in, but sometime around about March. And we'll let you sign up for that in December, so you'll have a couple of months to work on that. And as I'll explain later, the idea for that is you pick an article, which we provide a short list of articles for you to choose an article from, and you have to write a critical review of that article. So basically, can you explain what the article is about, and can you explain its strengths and weaknesses? And a key thing there is just, we're trying to see how well you've understood the article. So some people go a bit overboard on the strengths and weaknesses and just try and look for any trivial detail to pull out as a weakness and say, oh, they shouldn't have used a superscript here in the presentation, and that's like trying too hard. So what we're trying to see is whether you understand the article, and the critical side is an ability to demonstrate that you understand the science. And some of that might be the presentation. They may have presented the data in a biased way, so that would be a valid criticism. But picking up on every little detail of the presentation and not talking about the science would be a really bad thing. So basically, we're trying to see, do you understand the science, and that's what the course is about. So if you look on Canvas, which I'm sure you're all familiar with by now, so I won't labour that, you've got all these little tabs. Some of them are now empty because we're putting the information elsewhere. There's a description here of the assessment and feedback, which basically just tells you what I just told you, that there's two assessments. It does give you some guidelines for writing a critical review, but you're free to interpret and work as best you can with your own ideas of what is a critical review. Now, last year we had the timetables here, but I think you've all got personalised timetables this year. I don't really know how that's working. Well, no, the MRes haven't, but I think the Biotech have. Is that right? And the MRes have got all the timetables on the MRes handbook. So does everybody have a timetable and have access to it? Yeah. My only worry is now the lecturers, because as a lecturer you knew you could always go here and click and check what room you were in, and so I'm going to have to chase and make sure everybody's aware of where they're to be, because that's not there this year. This is from last year's Canvas page. I've just cut and pasted that. But if you've all got timetables, that's great. You know where you're going. We just have to make sure the lecturers do. And this is the timetable I've got and what it looks like. So this is me today. Your next lectures on Friday next week. We've got one in the morning and the afternoon. Rebecca Hall is going to be talking to you about cell culture. That's obviously important. Bacterial cells are relatively easy to grow. Mammalian cells are much harder. She's going to be focusing on mammalian cells and the conditions for growing mammalian cells. And then Matthias Solle is going to be talking about how to manipulate those cells and get genes into them or change the genes. So he's talking about transfection and microinjection. He's going to do a little bit on CRISPR as well. So it's about how you manipulate cells. Obviously, they're really fundamental techniques for molecular biology, cellular biology, being able to do stuff. And so it is through the whole course. If you look here, we've got a whole load of fundamental techniques for you to be able to do molecular biology. We don't cover everything because we can't in a course of this size, but we hope we cover all the most important ones, and other techniques you will pick up along the way from other situations. One important point here is that you've got these three lectures from Helen Cooper. These are actually, I think it's BioM 9. So the Biotech course, they do BioM 9, and Helen lectures on mass spectrometry there. And it seems stupid to reproduce those lectures in parallel on a second course. So these lectures here are all part of the Bio 09 course, and the MRes don't go to some of the lectures that Helen gives on that course. So you only go to the ones that are timetabled, and she will give you instruction, I'm sure, as well. Right, the next thing to make sure you all know, and you're probably aware of it anyway, but in case you're not, there's this little thing called modules, and if you click on it in that top left corner, you should be able to see all of the handouts related to the course. Now, this is my view of it, so this is stuff, you can't see any of this stuff here at the moment, because it's not been published. These two have been published, they're set to be published. And sometimes it's a case that we've got stuff on and we've not realised we haven't published it, we've uploaded it, so you might need to do as a lunch. So at the moment, there's a Word document which is a rough summary of all the techniques relevant to the course and some that are not even on the course, but are interesting techniques that you might use, and it lists advantages and disadvantages of the techniques. The table's not totally complete, but it covers most aspects of those things. And then the other thing is there's an exam paper. And the format may change slightly from year to year, but it's more or less going to be the same as this here. So it's got an exam paper with example questions. And actually I'll show you some of those towards the end of this lecture anyway. So you could go there right now and you could begin to see what we're going to be asking of you in March, and or whenever it is, not March, June next year. And then various things here will be made available online in the near future. So we've got the marking criteria, which I had in my head I wanted to revise, but then I looked at them again yesterday, and I think these ones are fine. I think it's the marking criteria for the essay I want to change. The papers for the critical analysis essay I just talked about will be made available as a list here. Later I've got to check all of those with the lecturers that they're happy with the list we've got here. And then it will be a maximum of 5 people per paper, I think. I'll have to check, it may be 6. Depends how many of you are. But we're trying to distribute. We don't want everybody signing up for one paper, basically. We want it equally between lecturers, otherwise we'll not get it marked in time. And that's annoying for some of you, because some of you will want a paper and you won't manage to get signed up for it. But sorry, that's how it is. Some of you will try really hard to get the paper you want and sign up, and still you won't quite manage it, but hopefully you'll get something you're interested in. Because, they're all interesting at the end of the day. Right, so that's where you get your information, and all the lecture slides, if you scroll down here, so I've taken a snapshot so it all works in PowerPoint, but if you scroll down in the real thing, in fact, if I find the real thing, if you scroll down you'll see that all the lecturers have got their own little section and nothing's published yet, and they may be changing what's there. So one thing is, although Dr. Cooper is giving the lectures on mass spectrometry, or Professor Cooper, sorry, is giving the lectures on mass spectrometry, Dr. Cunningham will be doing any coursework and any marking associated with this particular course. So these two lecturers are both doing the mass spectrometry between them. Helen's giving the actual lectures, and Debbie's actually doing the marking. So you'll find everybody here, but none of it's visible at the moment to you. That's just visible to me, and will be made visible to you at some point in the future. So lectures are supposed to be recorded. All the lecturers have been asked to record them. The university policy is actually, the university would like all lectures to be recorded, but some lecturers argue that this is not necessarily good teaching practice, and so there's an ongoing dialogue between the union and the university. So the university does not have an official policy that all lectures has to be recorded. It has an official policy that it would like all lectures to be recorded. So some lecturers may not record, so you can't 100% guarantee that all lectures on this course will be recorded. We ask them to be recorded. Most lecturers try to record them. Usually if it's not been recorded, it's just because there was a technical issue, but it's not guaranteed. If they are recorded, though, they will be in here, in this section, this being Panopto, and they should arrive here. So this lecture today is being recorded. It should arrive there. I'm told it's taking about 24 hours for the lectures to get fully uploaded to the system. So this lecture should be there in about 24 hours' time. And I will remind all the other lecturers to record them. In fact, I'll write a note to remind myself to remind them. But they are all lecturers are supposed to put their notes up for the lecture 48 hours in advance of the lecture now. That is standard university policy. So if some lecturer hasn't put their lecture notes up, all the slides up, before 48 hours before the lecture, you have every right to email immediately and complain. Particularly some of you have special adjustments and need to see the handouts at least 24 hours before. So 48 hours before you can already complain so that we make sure they're there 24 hours before. So feel free to do that. So I've already said this basically, that we'll put a sign-up sheet in December, which I've been doing on Canvas. I've been setting up a list on Canvas. And then I'll make it live at a certain time on a certain day, which I'll tell you in advance, and then you all rush, depending on how keen you are to get a particular article, to sign up for it. And each lecturer will provide a particular article for you to write about. Okay, so obviously this data is from last year's slide, so you can ignore that. Obviously we're going to be in fact 2 years ago, we didn't even know. So ignore that date. But it will be a 2-hour exam. There'll be Part A and a Part B. Part A carries 40% of the marks, Part B 60. Part A is a question of the format, I think I've got it on the next slide, let's just a quick look, of picking 2 techniques from a list that you're given. So there's usually a list of 5, and we ask you to describe the technique, and do you understand what the basics of the technique are? Do you know what it's used for? So what are the questions you can answer with it? And then what are the limitations of the technique? What is it particularly good at? What is it particularly bad at? So for example, bacterial cell culture, which we don't actually teach you, so it won't actually be on the list, but if we consider bacterial cell culture, well, we do teach you it because we do protein expression. And bacteria are used typically to express proteins because they're easy to manipulate and they can express proteins in very large volumes. But if you're expressing a eukaryotic, so that's the advantages of it. It's easy to culture a bacterial E. coli, and you can do genetic manipulation with it very easily, and you can produce protein in large volumes, so it's useful for crystallization. On the other hand, if you've got a eukaryotic protein and you express it in a bacteria, it won't necessarily undergo all the post-translational modifications that it would do in a eukaryotic cell. So that's a disadvantage, and it may not necessarily fold in the right way. And so you can begin to sort of discuss how it's a disadvantage to use a bacterial cell line to express a eukaryotic protein. And this is the sort of thing that this lecture course is about. It's not just about knowing there's a technique. It's about knowing where the technique's good to be used and where it's bad to be used, and how you would make some controls on the technique to see whether it's working in the way you want. Because most people will express a protein in a bacterial cell line because it is so convenient. But how do you check if you're doing a eukaryotic protein in a bacterial cell line? How might you check that it's behaving the protein in the way you want it to behave, and it is expressing properly? And how would you do it differently if you discover it's not working? So how would you express it in a mammalian cell line? So typically you would use a yeast, for example. Yeast has been well developed. Pitchia pastoris is a very good way for expressing eukaryotic cells, eukaryotic proteins, but it's much slower and it still has some limitations. And you might go all the way to expressing in maybe a human cell line, but that's much more complicated. So these are the things we want you to think about. And so this is very much what these questions are getting at. Do you know what the method is? But can you also tell us the limitations, both the positive things it's got, but also the negative things? And so that's what we want you to get out of the course, to understand the method, but also to start thinking about the limitations. And you can ask lecturers about that during the lectures. And you can do extra reading to work that out, and going to the literature and seeing what's been published in the literature is all part of the course, really. And then section B. Section B is really getting to what the course is about. Section B asks you to answer one of 2 questions. This is question 1 for the example paper. This is question 2. And so I'll give you a minute to read through that for yourselves, actually, if you just take time to read through that question. Right, so hopefully you've all read that. And obviously this question is actually a little bit like what I was just talking to you about, the fact that protein expressed from E. coli may be behaving in a different way from that expressed in the media, because the E. coli may not put in the right post-translational modifications. And so this is a question about how you would do the two different purifications and how you would do, what sort of tests could you do to check that this protein purified by E. coli is behaving in the same way as this protein in the natural state, and therefore you can use E. coli to produce large quantities of the protein you're interested in, so that you can do lots of experiments on it very easily, whereas getting it from the media surrounding the natural cells is going to be slow and cumbersome work and not giving you very high yield. And so this is, I'll let you read this one as well. This is a similar sort of question. So again, you can see, this is just really asking you how you purify a protein. But you've got the question of whether you're trying to purify straight from the kidney, or whether you're going to try and somehow get this protein expressed in E. coli. So if you want to examine the structure of the monomeric protein, for example, you may decide you want to express it in E. coli, so you've got enough of it to work with. And if you want to study how polymers are formed, you also may want to do something like that. So that's the sort of thing we want you to be able to do by the time you finish this course. We want you to be able to look at those sorts of questions, basically to be in a position where you can design your own experiments. And so it's not just about learning what you're told in the lecture and repeating them, which it shouldn't be at undergraduate either, obviously, but it's really now you're at master's level. We're getting you ready to be proper scientists. You can go in the lab, you can design your own experiments, and you can get on with it, and obviously that's what you want. Many of you are probably going to go on to PhDs or work in industry or something, and that's what you want from a PhD student or somebody working in industry, that you're coming in and you're designing your own experiments. And that you know the limitations of the techniques you're using, so you know if an experiment's not working, why it might not be working, and what other techniques might be available for you to use. So these are the marking criteria, just roughly so you can see. I say I might revise them, but I think these ones are okay now. I look at them. I think it was the essay ones I wasn't happy with when we used them earlier in the year. So the key thing here is you can get quite a good mark on Part A. Part A is just saying, explain the advantages and disadvantages of these techniques, describe this technique, and explain the advantages and disadvantages. And you can get really quite a good mark just by demonstrating that you understand the technique, and you've got the data in, you've been to the lectures and you've learnt it. But if you want to get the best marks, we do want you to demonstrate you've got a little bit more understanding than just the lecture course. That you've understood from reading papers or going to the lectures things that are relevant to this question. And then the Part B is really, again, it's not just looking at the question and saying, well, this is a protein purification question, but is there some detail of the question? So we're looking at, you've tailored your answer to the question in hand. So you're reading the question, and maybe the question says you need to purify a protein. And then a lot of students will just say, oh, protein purification, I express it in E. coli using the right vector, and then I sonicate and et cetera, and go through some purification thing that was just memorized from the lecture notes. But there may be some aspect of the protein or the system that we're using that we put into the question which requires a slight modification of whatever your standard purification protocol is that you memorised from your lecture notes. And that's what we're expecting you to pick up on. So, for example, it may be a eukaryotic protein, and if you then roll out a bacterial E. coli purification protocol, that's fine, you'll get some marks for it, but if you don't acknowledge that this is a eukaryotic protein and therefore there may be issues with using E. coli and what those issues are, then you won't get as many marks as if you just write a bacterial E. coli-based protein purification for that. So that's what, for the really higher marks, we're wanting to see that you're not just, to get beyond 60, you're not just rolling out your lecture notes because you've worked out, you've analysed the question, this is protein purification, and then structural biology here, so I'll just use X-ray crystallography, and now there we got the question done. What are the issues with the question? So, for example, if it's a structural biology question, well, NMR is not very good for large molecules. The magnets that we use now don't resolve the peaks for large molecules, they overlap too much. So you couldn't use NMR necessarily. But crystallography actually is also not that good for really large molecules because they're difficult to crystallize. But it's more applicable than NMR. So maybe electron microscopy would be a better choice, but you're not going to get the resolution. So these are the things we're expecting in an answer for you to pick up on. So this is what you should get out of a lecture from one of the lecturers. So how does the technique work? What problems can it solve? And this is an important one that a lot of people, for some reason, miss out because it's the basis of science. What are the controls? So, and if you're not getting that off the lecturer, you should be getting that out of the literature somehow. What controls are typical for this sort of experiment? So, for example, if you're using short interfering RNAs, it's very common to use just a randomized RNA sequence to go in with that as well, just to show that just putting some RNA into the system doesn't cause the effect that you want to see. And this is the basic question of science at the end of the day, isn't it? It's what is the competing hypothesis? So I'm doing an experiment and I've seen the result that I wanted to see, but is there another hypothesis that explains it? And so the basic controls are obviously your positive and negative controls. The basic control for seeing a negative result might be that I always see a negative result because I've screwed the experiment up. So I need a positive control to show that I can get a positive result. Equally, if I get a positive result, the basic hypothesis is I always get a positive result, so I need a control to show that I can get a negative result. And that's why you have a negative and positive control. But there might be other competing hypotheses that you also need to put controls in for in your experiments. And so you need to be thinking through what are the controls. Do I need to put a randomized piece of RNA in? Because maybe just putting RNA into this system gives me the result I want. Or do I... So what are the competing hypotheses that I could have which explain the result I'm seeing in my experiment? And so, when you're listening to the lectures, be thinking about how you control for the techniques they're using as well. Which is what this slide's about. So I've more or less said all of that, but I'll let you read that slide just quickly. And so this is really important. For example, with your critical analysis, the essay you've got to write, are there the right controls in the paper? Can you see an alternative hypothesis for the results they're showing for which they haven't done an experiment that rules it out? And that's the difficulty with science again, is when have you proven your case? How many experiments do you need to do to be satisfied that you've proved beyond reasonable doubt that it is how you think it is and your hypothesis is correct? Do you need to do another mutation? Do you need to do some structural biology to show it? Do you could always ask for more. And this is the argument you have when you're publishing an article with referees. The referees will often ask for extra experiments, and then often you write back and say, oh, that's just ridiculous. Clearly we've already done enough and we've already shown it. And then it's down to the editor to decide. Or sometimes you go, oh yeah, that's a fair point. That is a good alternative hypothesis. We do need to do that. Yeah, well, more of the same. So what are you controlling for? Really trying to think about your controls. There's an interesting thing here on randomisation. I've been talking to various of my research students about this recently for various reasons. People are often right, they do something randomly, and it's common in lots of articles. And what they mean often is not that they did it randomly, they did it arbitrarily. And these two things are quite different, and there's quite a nice way to demonstrate this conceptually. If I've got a cage with 5 mice in, and I'm going to do some experiments on those 4 mice, if I put my hand in and pull out a mouse, a lot of people think that's random. It's not random, it's arbitrary. The reason it's not random is that mouse, you might be getting that particular mouse because it likes to behave, to interact with humans, or it doesn't hide in the corner, or because it does hide in the corner and you're pulling ones out the corner. So there's a bias in the way you do that experiment if you just pull one out in what you initially might call a random act. If you want a truly random selection of the mice in that cage, you have to give each one a number and then generate a random number and pull out the exact one that you generated. That's random. But putting your hand in and pulling it out of the cage is not a random act. There are biases built into that experiment that you may not be aware of. So this is something you might want to consider as well when you're thinking about controls or how an experiment that somebody else has designed has been done. And often in a paper they'll just say random and they won't even explain what they mean by random, and it might be they've done it arbitrarily rather than randomly, and so you might get some biases there. Right, so that's me done. I said we'd be about half an hour, which we have been. Does anybody have any questions about any of this that you haven't explained? Yes?
Anything in the exam asks you have to be referenced?
Sorry?
Does anything in the exam have to be referenced? Or is it just...
No, we wouldn't expect you to cite citations in exams. I mean, I guess I'd be very impressed if somebody did and they were correct, but there's a good chance none of us are going to know what those citations are anyway, and we won't have time during the marking period to look them up. So, but yeah, if it's a particularly exciting thing that you're citing, it might be that I would want to look it up because of some particularly novel piece of research.
Is that common in all the exams that you don't need to cite?
Certainly here, yeah. We've never. None of.
I've always had to do that in my exams.
Have you?
Yeah.
Which university? Sheffield. Yeah, no, we don't require.
That's nice.
We don't require that, I don't think. No, all our previous undergraduates are shaking their heads no. I mean, if you're on an arts course, I can imagine that you would, if you're on arts or humanities, because there are, if you're doing philosophy, you're going to be discussing what some previous philosophers philosophized and then saying why it's useful or not useful and building on their arguments. Here, we don't want you to say that this work was done, Watson and Crick and Wilkes, 1953, structure of helix, nature.
That was always the last part.
Rosalind and Franklin, 1953, structure of helix. Yeah, no, we don't. No. Wow. Oh, that's impressive. No, I'm not sure what that gets you. I mean, that's just a bunch of names.
I think it was because they had to check that every reference is correct in the papers. At least one of them.
In the exams. What do you mean they have to track every reference?
You can fix the book.
You can make stuff up.
Yeah.
But surely they should know the materials so they know if
Well, I don't know, that's what they told us.
Factual.
But this was a couple of years ago now, so maybe we've changed things.
I mean, I would say that in an essay but in an exam, I mean, it's true. In an essay, we would always want citations for that reason. That if somebody's writing something and I've never seen it before and I think it's probably wrong, then if they've given a citation, I can check and go, oh, actually, no, I'm wrong and they're right because there's a citation for it. That's the point of citations in academic work. But in an exam, it just seems. If you were putting in something particularly peculiar that was not quite mainstream or hadn't been in the lectures, then maybe it would be useful to put a citation in, but it's not something I would expect. If I disagreed with what you'd written and I couldn't find a source, then I would disregard it.
Yeah.
If I knew it was absolutely wrong, then it didn't matter if there's a citation. If I know it's absolutely right, it doesn't matter if there's a citation.
But they still need to cite the reference in the particular study and what they did.
Yeah, well, yes. If you were talking about a particular study, then it would make sense to at least give some indication of who did it and what year. The thing is, now we've got Google anyway, so we can find most things. Like 100 years ago, you couldn't find references very easily, so it was really important. Citations were really important then. But now most things you can find Google anyway, or PubMed or whatever. But yeah, if it's a piece of weird stuff that you think nobody's ever heard of, it would be useful to put a reference in. Particularly recent work that maybe the
I
lecturer.
don't mean like the whole thing, I just mean like this name, 2015 or whatever.
Yeah. But then it might do if it's really novel, new stuff that potentially something not heard of, or a sort of an out-of-the-way theory that you've heard of, and it's not in all the main textbooks. But if it's basic material that you had in your lecture notes, anything that's in your lecture notes, the lecturer is going to agree with. That's what they told you. They don't need to check it out. But if you found an article somewhere that says something that's contrary to the lecture notes, or then probably yes, you should cite in that case because you're disagreeing with the lecturer. But as a general rule, no, I don't think we wouldn't expect you to cite. Certainly not for this course, anything I've marked. I mean, I'm not going to speak for all the modules, just in case. But I've not heard of it before and as a necessary requirement. But any other questions? No? Good. Well, I'll let you enjoy this bright and sunny day.